Coming up in this edition, every time a plane like this cuts through the air, it leaves tornado-like patterns of turbulence behind it that can disrupt or even crash another plane. NASA addresses the problem systematically and scientifically to make air travel safer. This is Skylab, a working laboratory developed by NASA to orbit the Earth, an endeavour that marked the transition from the exploration to exploitation of space. It may look like just another commercial airliner, but don't let its looks deceive. Instead of rows of seats and passengers, this aircraft carries a barrage of scientific instrumentation. And a very exclusive golf club. Those stories and more. These model airplanes have something in common with these real planes. They were all part of a NASA research program to learn about wake vortices, tornado-like patterns of air that trail behind the wings of airplanes, causing varying degrees of turbulence. The sheer energy of this wind turbulence left in the wake of larger aircraft has the ability to completely invert lighter aircraft that may be following. This is especially dangerous as craft approach for landing. While all aircraft cause vortices, large and heavy jets, such as the 747 and DC-10, create the more serious problems. Air traffic density around major airports adds to the severity of the problem. Because of the business of some airports, planes had to be sequenced behind one another so that a safe distance could be maintained to avoid the trailing vortex problem. However, this often resulted in increased fuel use and air traffic delays. Smoke generators mounted on the wings of these planes by NASA researchers made it possible to see and investigate the whirling air patterns. Research showed that by adjusting wing flaps at different angles and by making various design changes, the intensity of the vortices could be substantially reduced. But this wasn't the only research NASA was conducting. For 60 years, NASA has pioneered in aeronautical research. During World War II, the need was for real-time problem solving to respond to various crises. More recently, however, research was aimed at making planes fly higher, faster, farther, quieter, and with greater safety. It was little wonder then that research into the problem of wake vortices should be taken up with such enthusiasm. Research of these vortices range from studies like these at NASA's Flight Research Center in California, where different combinations of gear and flaps were used to break up the vortex, to an experimental laser system at the Marshall Space Flight Center in Huntsville, Alabama. Working with the Federal Aviation Authority, the experimental laser program was an effort to develop an accurate vortex detection and monitoring system that would permit tracking the path of vortices produced by large aircraft. Field tested at the John F. Kennedy International Airport in New York, the laser research was specifically aimed at making commercial air traffic safer. Information gained by flights of the 3,500 km/h YF-12 helped the designers of new aircraft and spacecraft. Heating, stability, and control aircraft loads. These were just a few of the many tests that employed the high-speed planes as flying research tools. The rocket-powered X-24B completed 36 missions over the desert near the Flight Research Center, which brought to a close experimental rocket-powered flight tests that began with the XS-1 in 1946. These unique planes proved extremely valuable in advanced aeronautics research. Using the same aeronautic know-how harnessed to design sleek high-speed jet planes, NASA engineers cooperated with the Department of Transportation to test a variety of fuel-saving modifications for large trucks. Even some simple changes resulted in a 40% reduction in aerodynamic drag, which is the wind resistance that forces the truck engine to work harder. This translated directly into a highway cruise fuel reduction of 20 to 25%, an interesting ground transportation problem being aided by aeronautic research techniques. Wake vortices, of course, are especially dangerous for small aircraft. Hence, the crashworthiness tests at NASA's Langley Research Center were at least in part driven by the need to reduce the number of accidents that arose from light aircraft following too closely in the wake of heavier planes. Another important element in reducing aerial fatalities was the education of pilots, and instrumental in that has been the flight simulator for advanced aircraft. What the pilot sees and hears in this simulator at NASA's Ames Research Center is like the real thing. All just part of NASA's long history of research aimed at improving the quality and safety of flying. This is Skylab, a working laboratory developed by NASA to orbit the Earth, an endeavor that marked the transition from the exploration to exploitation of space. Skylab was 15 meters tall, 8 meters across, and had some 1,000 cubic meters of working space. Skylab was divided into a lower floor with crew quarters, wardroom and medical experiment area, with the upper floor dedicated to space technology equipment. The multiple docking adapter provided docking ports for the command module, as well as housing the control console for the solar telescopes and a series of cameras for conducting Earth observations. The unmanned orbital workshop was launched in May 1973 atop a Saturn V rocket. But very early on, it became clear that the rapidly mounting temperature in Skylab was due to the meteoroid shield being torn off by the slipstream during launch. Also, the lab's solar array panels had not been deployed. Of course, the launch of the first Skylab crew, due the next day, had to be postponed until solutions could be found. The urgent need was to stop the rapid temperature rise, which was achieved by reorienting the satellite so that it was no longer broadside to the sun. The next 10 days were hectic. Teams were immediately formed to find solutions to the problems. A major objective was to design and fabricate a thermal shield that could be deployed on the workshop to make Skylab habitable. Throughout the United States, teams worked round the clock in an all-out effort to perfect such a design. Meanwhile, at the Marshall Space Center in Alabama, crews were evaluating the installation of a parasol device in the Skylab underwater simulator. In conditions that approximated zero gravity, they also trained underwater in methods of freeing the jammed solar panels. But the actual work would have to wait on an eyewitness assessment by the astronauts in space. Time was becoming critical if Skylab was to be saved. Relief would come only from the thermal shield parasol, which would be deployed by the astronauts when they reached Skylab. 10 days after the initial launch, astronauts Conrad, Kerwin and Weiss were on their way to Skylab. It was the first step in the fulfillment of an opportunity to use men in space for practical, humanistic benefits. After rendezvous with Skylab, a televised fly-around was performed to assess the damage. Most of the predictions were confirmed. The meteoroid shield had been ripped away, exposing the workshop's skin to the sun. One of the solar array panels had been completely torn off, and the other, only partially deployed, was jammed by a fragment of the damaged meteoroid shield. An unsuccessful attempt was made at freeing the panel before docking with the workshop. After a night's sleep aboard the command module, the astronauts entered the workshop and took steps at deploying the parasol. In mission control, optimism that the mission could be saved wasn't long coming as Skylab temperatures began dropping rapidly. The parasol was doing its job, but there was still a shortage of electric power. The stuck solar wing had to be pulled out fully. But thanks to the work of the backup crew at Marshall, the procedures were worked out for freeing the solar panel. Astronauts Conrad and Kerwin went on their first spacewalk to repair the damage. This took 3.5 hours and was difficult work, but they prevailed and were able to sever the obstruction and pull out the panel. Within hours, the power situation was nearly normal. The mission could continue, transformed from near ruin to success. One of the innovations new to this mission into space was a series of life sciences tests. This lower body negative pressure test provided valuable information on the cardiovascular system. This was a measure of motor sensory performance, an experiment designed by a high school student. Using a punchboard apparatus, the crew's hand-eye coordination was measured on a daily basis. Balance, orientation, and perception, so important to man's ability to function efficiently in space, was another of the life sciences tests. The astronauts were instructed to exercise frequently, and one of the methods was the ergometer or bike to help keep them in shape. This also served as a test for changes in metabolic activity while working in micro-G environment. Throughout each mission, a vast number of tests were made on the eyes, ears, nose and throat, and blood samples were taken and returned for post-flight testing. Skylab also gave astronauts the opportunity to test materials under microgravity and vacuum conditions. The formation of crystals was the most valuable of all the manufacturing experiments. It resulted in crystals 10 times larger than those grown on Earth, with a much better uniformity of composition, so important in the field of electronics. The aim was to develop electrical systems that would perform more functions, be faster, smaller, less expensive, and require less power. But it wasn't all work. The astronauts had a lot of fun. Even something simple like blowing bubbles was a whole new experience in space. They could puncture them, pull them, pick them up, but they still wouldn't break. As can be seen, getting from place to place was no problem in Skylab. Weightlessness itself can be lots of fun, as Pete Conrad demonstrated. No circus performer or Olympic acrobat could match this. Whilst, as you'll see later, Alan Shepard was the first to play golf on the Moon, This was the first spaceball game ever played. The first 3 tenants of Skylab returned to Earth after 28 days in space. Despite the adversity, it was a successful and novel mission in space. From a distance, it looks like any other plane coming in for a landing. The similarities end there, however. Inside, this jet is filled with highly sophisticated science experiments, a laboratory with wings. Called Galileo 2, the Airborne Science Laboratory flew its missions from NASA's Ames Research Center in California. It's seen here landing in Melbourne, Australia. One stop in a globe-spanning experiment from pole to pole to see if there were changes in our upper atmosphere caused by gases used in aerosol cans and other pollutants. There were 8 different experiments either in or on the plane. Some collected samples from probes mounted outside the aircraft, and with the onboard computer, many were analysed on the spot. Others were bottled and returned to the laboratory for additional analysis. Scientists were collecting information on everything they could detect in our atmosphere. From the Earth up, aerosols, jet flame exhaust, anything that might adversely affect our planet. From space, they measured cosmic rays and charged particles. Even measurements of water vapor were proving to be helpful and were instrumental in further studies of air turbulence. All the data taken was studied in greater detail by universities and research centres around the globe. Surveying atmospheric pollution from an airborne laboratory, a cooperative effort to study the effects of pollution on the overall atmosphere and on life here. Russia's space program began with the launch of the first satellite Sputnik on October the 4th, 1957, to mark the 40th anniversary of the October Socialist Revolution. The next step was the first manned flight on April the 12th, 1961, when Russian cosmonaut Yuri Gagarin blasted into orbit and flew around the Earth. The construction of the Mir space station was another scientific and technological achievement. The first module of the space station was launched into orbit on February 20, 1986. Less than a month later, the first crew, Leonid Kizim and Vladimir Solovyov, were making themselves at home. The designers of the space station had intended their creation to last from 3 to 5 years. But Mir's life happened to last almost 4 times longer. Mir has made over 85,850 spins around Earth in the 15 years of its existence. Several international crews had worked on board Mir. During its 1.5 decades, many lifestyle and scientific experiments were conducted. Much information and knowledge has been garnered from the experiments and research conducted on the Mir spacecraft. The experiments took all forms, all shapes, and all sizes. Here, an open solar antenna floats free, creating a magical scene with our beautiful planet below. On February 24, 1997, Mir had its first serious accident. A fire broke out when cosmonauts tried to change an air filter, forcing the international crew to wear gas masks. Several months later, a Progress cargo ship hit Mir during docking, puncturing one of its modules and damaging solar batteries. In September 1997, a computer failure sent Mir spinning out of orientation from the Sun, and it was a nervous 24 hours before Mission Control regained control. Hope for the Mir space station came from the US, Some investors pledged to pay $20 million to continue the Mir program. A month later, a cargo spacecraft delivered fuel and supplies to restart the space laboratory. Later, a two-man crew returned to the space station to adapt it for tasks ranging from industrial production and scientific experiments to space tourism and advertising in orbit. But all efforts to prolong Mir's life came to nothing. Equipment failures continued, and promised private investment failed to materialize. Despite protests, the sinking of Mir, once the symbol of Russia's space glory, was inevitable. Its scheduled splash into the Pacific in March or April 2001 was given the go-ahead. And finally, if you think your golf game is up to scratch and you're looking for an exclusive club to join, then look no farther. This is astronaut Alan Shepard hitting up on the 16th on the moon. Just watch that swing, see his style. Of course, note the exclusive uniform which has to be worn at all times when playing here. Not bad when you consider this is a 5,500-yard fairway and a par 19. Some might say it's a good moonwalk.